On va accueillir le professeur Daniel Gale. Can you hear us? I hope so.
Yes, I can
Yes.
hear you. Thank you.
Very good. So we are very happy to welcome Professor Gale, who is professor in nephrology in London, who is an expert in inherited renal diseases, and who is heading, I think, the RADAR database. And so if you can let us know everything regarding Alport syndrome and the RADAR database, the floor is yours. Thank you very much.
Thank you. Thank you very much for the invitation to talk. I've just discovered that I have to quit and reopen Zoom to be able to share my slides. So I will join you again in 1 second. I'm sorry about that. Great, fantastic. So yeah, I'm sorry about that delay. I've got a new computer and I had to do something to enable that. Firstly, thank you for the invitation to speak, and I'm sorry I'm not able to be there in person. I'm also sorry that my French is not good enough to participate in French, so you'll have to follow me in English. So thank you for that. So RADAR is the National Registry of Rare Kidney Diseases in the UK that was established by the Renal Association in 2010, initially with small-scale funding from both the Medical Research Council, Kidney Research UK, and also Kidney Care UK, the patient charity for people with kidney disease. It now includes over 100 disorders divided up into around 30 rare disease groups. And each rare disease group is represented by clinicians, by patients, including patient support groups, and also academics. And we've got a community and a set of resources, and we have regular meetings. We've got a web page which you can find listed here. And we also have a patient registry, which is what I'm going to be talking about for the rest of this talk. So we've now been recruiting for over 13 years. We've got around 30,000 participants from 108 hospitals right across the country. And these data are publicly available. You can navigate to them on our website showing the various different disorders, the largest being ADPKD, and then there are progressively smaller sets depending on how rare the disease is. And Alport syndrome, we've got almost 1,000 people registered. So to participate in RADAR, all participants sign an ethically approved consent form, which gives us consent to access, analyse and store their past, present and future medical record. It also provides consent to link to other databases and registries they're part of, and consent to be informed of future research studies that they might be eligible for. We'll come back to that a bit later. All the data that we hold are held and processed at a central site hosted by the UK Renal Registry, which was established back in 1995 to collect data from all UK centres delivering dialysis and transplantation, really as a quality assurance process. We built on the existing database and informatics infrastructure from this, which has allowed us to develop automated data feeds from all the renal units in the country, and also gives us very good capture of initiation of renal replacement therapy and death events via the Office of National Statistics. In terms of how this registry has developed, we have broad, very simple and publicly available eligibility criteria for each disease, which you can find on our website. The National Institute of Health Research, which is a government-funded organisation that aims to facilitate clinical research in the UK, was responsible for the Recovery COVID trial. And it provides a small amount of infrastructure based on recruitment to ethically approved research at NHS sites, meaning that individual NHS sites, hospitals, are incentivised to recruit patients to studies such as ours. However, they're not resourced to input data. They just get a small amount of money per patient recruited. Because of this, we've had manual entry of very few fields at recruitment, and most of the data that we've got comes from automated data feeds, either from the participating sites and also from central molecular genetics labs. And we've avoided a lengthy wish list of clinical data entered manually by sites because we felt that this would impair recruitment. So how does data enrichment work? Well, what we can do is go back to sites, particularly ones that have recruited large numbers of patients, and asked their informatics team, so their hospital laboratories, to send us the historical data. And this histogram here is an example of an enrichment exercise that gave us old lab results from some patients going back to the 1980s who were participating in RADAR, illustrating the power of the approach. So we've done a number of different studies. We've done genetic association studies, again, in collaboration with the NIHR Bioresource, which is a whole genome sequencing study. Some of those came out a few years ago. We're also doing retrospective and prospective longitudinal cohort studies to look at natural history, outcomes, and clinical practice in rare diseases. We can also do some work with randomized controlled therapeutic trials, and I'll talk a little bit more about that in a few minutes. We can do registry studies as well to look at epidemiology. So what do our data show? Well, this slide summarizes renal outcomes in patients with various glomerular diseases. And I put this up as a sort of example. And I draw your attention firstly to the large numbers in each of these categories. So 2,500 with ANCA-associated vasculitis, another 2,500 with other vasculitides, membranous similar size, MPGN over 1,100, and IgA nephropathy 4,000. And what you can see is that the burden of kidney failure disproportionately affects young adults and young people in some of these glomerular disorders, whereas membranous and vasculitis tend to be later onset and tend to respond better to treatment. And this is a sort of whole life course with large numbers even out to the 9th decade in some of these phenotypes. Importantly, when interpreting data like this, people have to survive long enough to get into the registry, and also they have to be ascertained. So there are some mechanisms of bias that could exist in a registry-based study such as this. So it's important to bear that in mind. We've also looked more detail at end-stage kidney disease in IgA nephropathy, and what I'm showing you here is that renal survival, regardless of the decade really at which the patient is diagnosed, is pretty similar and pretty poor. And we can also look at time average proteinuria in the first 6 months or year of diagnosis. And again, we see the expected very poor outcomes in people with high-grade proteinuria. But interestingly, even in individuals with less than approximately a gram a day of proteinuria, we do see very poor renal survival if you take it out long enough this slide here goes up to 15 years, but clearly once you're getting out to 20, 25 years, renal survival starts dipping below 50%, even in the group with very low-grade proteinuria. So this is data from the IgA nephropathy cohort. What does this mean in practice? Well, given how young people are when they tend to be diagnosed with IgA nephropathy, we really need a very slow rate of progression in order to avoid kidney failure at some point in these people's lives. And if you look at just the group of people diagnosed in their 30s and 40s, which is common for IgA nephropathy, even those declining at 1 ml per minute per year, around 40% will end up needing renal replacement therapy or dying prematurely. And you really need to get down to very low rates of progression if you're going to avoid that outcome in the vast majority of patients. So we can also look more generally at rates of EGFR loss, and this slide is showing you the numbers and the mils per minute per year median EGFR loss in each of these cohorts. So adult onset diseases, 3.6 for ADPKD, 5.8 for monoclonal gammopathy. And again, children, the numbers are much lower, particularly for some of these. But again, you see very rapid progression of renal disease in some of these phenotypes. And this contrasts quite sharply with the general CKD population, in which rates of EGFR loss tend to be much, much lower. So in the SHARP CKD study of ezetimibe, published a few years ago, the average loss of GFR in a group comprised disproportionately of people with cardiovascular disease and diabetes was very much lower than we see in these rare kidney diseases, which is perhaps unsurprising. So we can also look at EGFR loss, but rather than plotting the rate of loss, we can do a survival analysis to look at survival to EGFR above an EGFR estimate, which is what's shown on the x-axis. And what you can see here is that different glomerular diseases progress at rather different trajectories. So some of the diseases present with well-preserved EGFR, so SRNS or FSGS typically, and progress quite rapidly. Some present with severely impaired GFR, so ANCA-associated vasculitis. Median EGFR at presentation is around 40, but progresses rather slowly. And IgA nephropathy presents with a low GFR and progresses rapidly, which again is borne out by the poor renal survival figures I showed you earlier. We can look at the time spent in what we've termed the therapeutic window. So this is a window in which there might be amenable to or eligible for clinical trials. And we can see that while membranous and vasculitis, on average, people have a decade in this window between 75 and 30 mils per minute. In IgA nephropathy, this most patients traverse through this very rapidly. And this probably reflects or explain some of the difficulty we've had historically in recruiting patients to trials in these diseases. So what about Alport syndrome? Well, we've been recruiting for the last decade for this disorder. Nearly 1,000 patients recruited. The majority have X-linked Alport syndrome with 400 males, 300 females, small numbers with autosomal recessive, and a few patients with what's termed clinically as thin basement membrane nephropathy or heterozygous autosomal Col4 defects. We've been able so far to get genetic reports. So these are validated reports issued to patients for around a third of the patients. And unsurprisingly, 85% of these reports did provide an explanation for the patient's disease, with around a third of the remainder having a suspicious variant that wasn't clinically reportable. And then, again, there's a mixture of missense and protein length altering variants among these reports. So I'm showing you on this slide the median age at diagnosis by genotype and also by sex. And you can see that for X-linked and heterozygous Col4 variants, whether they are protein length altering or missense, diagnosis tends to be made around the third decade of life on average. Obviously, there's a bit of a spread. However, in autosomal recessive disease, protein length altering variants tend to present much younger than people with one or two missense variants. We can also look at renal survival in the Alport syndrome cohort. And again, this won't be hugely surprising to people familiar with the Alport's literature, where autosomal recessive and males with X-linked Alports have a rather poor renal survival, with median age at kidney failure around 33 or 24 years, respectively. With renal survival being better, but still by no means normal in X-linked females and also heterozygous individuals. We've also looked at the nature of the genetic variant, and in males with X-linked Alports, we see the expected reduced renal survival or younger onset kidney failure in individuals with a protein length altering variant compared with missense variants. But interestingly, in females, and it's very small numbers, only about 70 patients, but we see actually no end-stage renal failure events among the females with protein length altering variants. And I think there are a couple of biological explanations for this, but of course it's a single study and rather low numbers. So be interested to see if this is borne out in more international studies in the future. Again, we've looked at the small number of patients with autosomal recessive disease, and again, we see at least a trend towards more severe disease in people with protein shortening variants. This slide is showing you the trajectory of renal function loss, again, using the survival analysis that I showed you earlier for the glomerular diseases. And again, you can see the rather more rapid, more severe disease in males with X-linked disease compared with females, and again, with heterozygous autosomal variant carriers. And there's still a large amount of time in the therapeutic window, certainly more than IgA nephropathy. But again, what's interesting here, to me at least, is that the trajectory doesn't look quite as linear as some of those other disorders. And that may be a function of the rather small numbers of patients that we've got, but may also represent some genuine differences between this disease and some of those other disorders that I showed you. So as well as analysing natural history and renal outcomes, we can also use radar to inform clinical trials. Firstly, we can identify those diseases with the greatest unmet need, so those with particularly the young onset kidney failure and the high burden of renal replacement therapy need. We can also look at the disorders in which the EGFR is rapid enough to be a feasible trial endpoint for even a rather short trial with small numbers. And regulators, healthcare funders, and clinical trialists really need this information if they're going to get the most out of the small populations in rare diseases that exist. We can also assess the feasibility of recruitment to a trial. So if somebody writes a clinical or proposes a clinical trial with very stringent eligibility criteria, we can look in radar and give an opinion as to how likely we are to be able to recruit to such a trial. And this can reveal gaps in our knowledge, but also it can potentially inform estimate of the potential market size if the clinical trial then goes on to lead to licensing of a new drug. And this has been a somewhat iterative process in that the analyses that we've been doing on the natural history have really helped to inform clinical trials so far. But in addition to trial feasibility, we can also help deliver clinical trials. Because we've got the geographical data, we can identify sites and regions in the country where there are large numbers of patients likely to be eligible. And because we've got permission to consent participants, we can directly contact individuals and their clinicians to tell them about a clinical trial that they're potentially eligible for. And in fact, this is an important motivator for many people to sign up to radar in the first place, the ability to participate in an interventional trial that they might otherwise not have heard about. And we've done this in Alport syndrome for a trial of a drug that is that allows the ribosome to read through premature stop codons delivered to males with X-linked or autosomal recessive Alport syndrome. And this agent targets only certain types of premature stop codons. And the trial eligibility criteria regarded a very well preserved EGFR and high-grade proteinuria. So you can see that even though we've got large numbers of people with Alport syndrome, once you look at those with certain types of premature stop codons and well-preserved kidney function, this is a very difficult trial to recruit to. But we were able to find patients looking nationally. And in fact, this is a press release by the company that came out just last week, reporting that one participant in this study had gone into sort of proteinuria remission following dosing with their agent. So this is somewhat encouraging from the clinical trial point of view, but from radar point of view, it provides proof of concept that we are able to identify patients and get them into clinical trials, even where the criteria are rather stringent. So what I hope I've told you rather briefly is that radar is a source of real-world data about patients with rare kidney diseases. We're currently analysing the epidemiology, natural history, and predictors of outcomes across a large number of phenotypes. Radar can act as a catalyst for clinical trials. There's much more we want to do: integrate genomic, biomarker, and interventional studies, link with other sources of data, particularly hospital episode statistics, which will give us information about comorbidities. We're analysing socioeconomic deprivation index of our participants, ancestry, ethnicity, and pharmacogenomic associations. And of course, particularly for the rarer disorders, we're going to need international collaborations of similar registries to get new insights. So what we found is that early and full engagement with the patient groups has provided powerful momentum for many of the rare disease groups. Assembling cohorts and collecting a rich enough phenotypic data set has required a distributed recruitment pattern and participation across disease areas, really on a national scale. But given that every country, every health service is different, the solutions in other countries are going to be rather different, I suspect, to what we've been able to do in the UK. And we've also discovered that big data collection and processing, as well as the analysis, presents its own challenges and has needed a lot of support. So I'd like to acknowledge firstly the funders of the radar registry, the MRC, Kidney Research UK, Kidney Care UK, all the participants and their families, and the various operational and analyst teams, as well as the clinicians and informatics teams right across the country. And I'm very happy to take any questions. Thank you.
Thank you very much. That was very impressive. I don't know whether there are questions in the room or in the chat. Bertrand Knebelman.
Hello, Danny. Can you hear me?
I can. Hi, Bertrand.
Yes, thank you so much for this wonderful presentation. We are very impressed by the radar data here in France. It's very impressive. I was wondering, in terms of granularity in your database, do you have data on the proteinuria and the trajectory of proteinuria compared to GFR, and also on the treatment the patient receive in terms of RAS inhibitors and GLT2 inhibitors?
Yeah, we've got quite good proteinuria data, and we've analysed that or we publish our analysis for IgA nephropathy, looking at there's obviously lots of different ways one can analyse proteinuria. So that, because it's frequently tested by clinicians in standard practice, and it's tested by biochemistry labs that we've got data feeds for, that we can get with quite good coverage. Medication data, we've also got pretty good coverage for that. It's a bit more patchy because it depends on the electronic prescribing or not, or the mechanisms by which that data are captured at the individual units. So that's getting better, but historically it's been less good and a bit more patchy. So not as good as the biochemical indices. We can do manual supplementation of data, but that requires resources that we're sort of getting and negotiating from various sources. So yeah, there's a lot more that we can do than I've shown you already.
Thank you. Another question. I was wondering regarding the funding. I understood it's national funding. At the beginning, was it determined for some time? Is it something which is reevaluated regularly or not? How does it work?
So the funding, there was an initial grant from the MRC, Kidney Research UK and Kidney Care UK. It was not, I don't know the actual figure, but it was not a huge sum of money that allowed the initial infrastructure to build the database in the renal registry. But the bulk of the funding has come from the National Institute of Health Research, and that's not gone to RADAR at all. That goes to the individual sites. So they get a small amount of money as a sort of incentive to recruit to clinical trials, any clinical trial that's adopted by the NIHR. So I mentioned the COVID recovery trial, and this infrastructure, again, it built up. So the idea was, going back sort of over a decade and a half, to build up clinical research infrastructure across the NHS by incentivizing research activity, even for hospitals that are not kind of driving, not academic centres that drive research. They still can recruit to research, and they can do that and deliver interventional studies. So, for instance, an interventional clinical trial will get a lot of money from the NIHR to support the research nurse activity. Recruiting a patient to a registry study is a one-off payment of, 20, 50 or £100, depending on various things, that goes into the budget of that local site. So we're not talking large sums of money, at least initially, but over time, it's built up to a large amount of money. And it means that a small district hospital will say, well, we could put all our rare disease patients, which is what all our renal rare disease patients, and there's actually lots of them, and so that actually allows it just boosts their research capacity. So that's the sort of funding model that we've had. It's very decentralized, and we're fortunate in that there's been that kind of big investment on a national scale that's allowed this to happen.
Thank you. I don't know if there are no other questions. I don't see any questions in the chat either. I understood patients can contact the radar in order to know whether there are currently trials or so on, but how much the patients are involved in data collection or reporting their own data or not?
So we're just implementing this, where so it's not operational yet, but we've designed and we're building a system for patient entered data. And we're doing, as an initial test, a survey on kidney pain, which is going out to all radar participants, and we'll be able to compare that across the different phenotypes. And we will also allow patients to input their own biochemistry data that they may have that's not captured by the hospital labs. For instance, if they've moved hospitals, which is obviously a particular problem, people moving from pediatric to adult practice.
Okay. Oh. C'est que l'argent. I'm sorry, I'm speaking in French just for a few seconds. L'argent va au site qui vont recruter des gens pour saisir les data, et que justement le funding est finalement très décentralisé, contrairement à ce qu'on fait ici. It was a question from a patient association regarding the centralization and who is getting the money and how is it working to really to collect data and complete the base itself, and which is a problem we're facing in here.
Yeah, it's very difficult getting data to be put into a research registry manually across large numbers of centers. People just don't, the resource that you need to do that is huge. Yeah.
But we can congratulate you.
Thank you.
It's really impressive. Okay, thank you so much.
Thank you. It's great to be here.
On va passer au topo.